Let's see. Okay, so I'm using a different camera this time, and I believe the audio should be built in. Can you guys just let me know if you're able to hear me or not? Because I want to see if the mic's picking me up. Okay, awesome. If you need me to speak up, just let me know. I'll try to project as best as I can. So today I'm going to be going over ions. Okay, awesome. This is actually what we were going over when we left school, and I know that this is something that caused confusion about bonding, and like we were going over the swap and drop. So we were taking elements from the periodic table and we were creating ionic bonds. So in the previous video, we kind of left off with like ions versus isotopes. So I'm just going to pick up from there. But we are done with isotopes, so we're just specifically going to talk about ions because now we are in the bonding unit. So this is review, but I am going to be building on it a little bit just to make sure you guys get a solid foundation, because we were still, like I said, in that stage of, okay, I'm kind of getting this, but I'm not totally getting it, okay? So here's what's on the agenda for today. I'm going to be going over ions and charges. I'm going to be going over ionic bonds, how to do the swap and drop. So basically, how do we get from charged ions to a bond, specifically an ionic bond? I will also discuss covalent bonds, and then we'll look at, okay, well, how do I know if I'm looking at an ionic bond versus a covalent bond? And that is kind of the new thing, but I think that's something that you guys will catch up on really easily. Yes, so as far as the Zoom question, so I'm going to be using Zoom for office hours, and I'm going to be using this, the YouTube channel for teaching, because immediately as soon as I'm done, like it saves a video and then posts it to the YouTube channel. But since you mentioned that, would you like to have like a Zoom like class, like so you can see me and hear me and I can see you too? Okay, let's do this then. How about we try 30 minutes on here? So roughly till like 2:30. Like I'll just say what I have to say here. So I won't like ask you any questions. I'll just do straight lecture. I'll just kind of break down what everything is, give a, and, you know, maybe just give a couple basic examples, but I won't even get into examples. And then let's say we cut it at 2:30. And then on Remind, I'll send out a Zoom link, and then we'll do examples together live like that. What do you guys think about that? You want to try it? And you don't have to show your face on Zoom, by the way. You can like hide your face and you can mute yourself if you don't want. Hey, Mr. Bumpers. Okay, then that's what we'll do. So for anybody who just came in at 2:30, and it's gonna have to be a little bit beyond 2:30 because I kind of started a couple minutes late, but I'll let you guys know, like, okay, lecture's over, let's go to Zoom, here's the link. And you'll have to give me a couple minutes to create the link, but I'll send it out and then we'll have kind of like a FaceTime session, okay? Okie dokie. All right, so let's get started. Okay, so last video we left off on ions. If you need me to write bigger, please let me know. Because I want to make sure you can read it. I saw that the last video was like really grainy. I noticed people were having trouble seeing what I write, and it was like poor camera quality, so this one's a little better. So if you can't see what I'm writing, just let me know, okay? All right, so we are going to start off with ions. So an ion is a charged particle. So keep in mind we have two charged particles in the atom. We have protons and we have electrons. We have protons and we have electrons. So ion just means a particle that is charged. Now you can use particle to replace the word atom, okay? So atom is really what we're referring to. So an atom that carries a charge. So an ion, I'm gonna put the definition down here, is a charged particle. That being said, you can have two charges. You can have a positive charge and you can have a negative charge. So if you are talking about a positively charged particle, that is called a cation. So yes, cat as in like kitty cat, as in a kitty cat has a paw. So positive cat case meaning negative. Okay, so when we are talking about a cation or anion, we are talking about an atom that has a charge. Now, the way that it gets its charge is it either gains electrons or it loses electrons. We cannot gain or lose protons, okay, because that means we're just talking about an entirely different element. When we're talking about bonding, only electrons, okay? So in order to get a cation, to get a positively charged particles, that means electrons are lost. So I'm going to say lose electrons. So it could be one, it could be more. All right, and so with anions, if an atom is to become more negative, that means that it is gaining electrons. Okay, so an ion in general, we got charged particle, two types of charged particles. We have our cations and we have our anions. Now, by looking at the periodic table, you can already tell which element will become a cation and which element will become an anion. So initially, before bonding occurs, all these elements are neutral. Remember in the previous unit, in the periodic table, we were talking about how proton number equals electron number. Well, an element just sitting there by itself, not reacting with anything yet, is going to be net neutral, meaning protons does equal electrons. But as soon as an element bonds, okay, when two or more elements come together to form a compound, that is when the electrons start to get lost, and that is when you start turning into ions and where the charges come from. So we have our alkali metals, group 1. As you can see, it has a +1 charge. That literally tells you that the ion is going to be a positive ion. So the alkali metals turn into a cation, and all of these elements in the alkali metal group or group 1 will have a +1 charge, meaning it loses 1 electron. It will give 1 electron away. All right, in group 2, we have our alkaline earth metals. This group has a +2 charge, meaning 2 electrons will be lost, will be given away, and therefore it forms a cation when bonding. Group 3 has a +3 charge, once again, cation, 3 electrons will be donated. Now this group, we're not really going to talk about this group right here, the group with carbon in it, because they could act as like donors or acceptors of electrons. You're not really going to touch on that until next year when you take chemistry. Keep in mind, this is physical science, so I'm going to stop like in the realm of physical science. Okay, so, but that is plus or minus 4, depending, okay, just depending on what it's bonding to. Group 5, you have a charge of -3. Now we're in the anions. So once the elements in group 5 bond, they turn into an anion or negative ion, and it has a -3 charge, meaning it gains 3 electrons. Now group 6 gains 2 electrons because it has a -2 charge. Group 7 gains a -1, gains 1 electron, which is why it has a -1 charge. Now notice, and group 7 is your halogens, by the way. And then group 8 is your noble gases. Notice Group 8 has a charge of 0. That is because group 8 will not react, okay? They are already stable. The entire purpose of every element on the periodic table for it to bond is to have the stability that group 8 has, okay? So group 8 does not have to bond, and it already has a full valence shell. I may have mentioned before, neon and down has 8 electrons, and then helium is an exception. It only needs 2, so it's happy with 2. But all of these in the noble gases are stable. So that's why these elements are going to either give electrons or take electrons, so that at the end, they can all have a charge of 0, like a net charge of 0 for the whole compound or molecule. And then each element in its own way can have its full valence shell, which is usually 8 valence electrons. Okay, so if you will notice, there's a pattern on the periodic table. And I told you I'm all about patterns, okay? So notice starting at group 5. You have group 5, and it gains 3 electrons. Well, I told you guys that the magic number is 8, right? So if you have 5 valence electrons already, and then you take 3 more, you end up with 8, right? So group 6, you started with 6, you gain 2 more, now you have 8. Group 7, here's the pattern. As soon as you see 3 of the same pattern in a row, it's going to keep continuing. So that's, going to be your pattern. So you have 7 electrons, gain 1 more. Now we have 8, we're stable. So basically for group 5, 6, and 7, you're like, oh, well, how far away am I from 8? And that's really what determines the charge. And then the same thing is true for group 4, because it is plus or minus. It could be cation or anion. So really group 4 and above. And once we get to 8, hey, I don't need any more. I already have 8 valence electrons. But then group 1 to 3. Group 1 to 3 doesn't quite follow that pattern because it's talking about giving, not taking. So the pattern I'm describing is talking about, okay, if I accept this many, I already have, so many electrons, now I'm going to get to 8. Okay, so groups 1 through 3 are like, oh, this is how much I'm going to give away. Now, why is it group elements in group 1 to 3 are cations? So it has to do with energy. Okay, so whatever requires the least amount of energy is the direction the situation is going to play out in. So, like, for example, we went over stuff in like the work unit, like which of the following makes work easier? Well, using a simple machine. If it's easier for me to push a box up a ramp as opposed to lifting up a really heavy box, I'm going to use a ramp. So this is kind of the same situation. At the end of the day, all chemistry, all physics breaks down into energy. What requires the least amount of energy? What is the most energy efficient? Where does the energy go? That is what all of the science is all about. So in groups 1 through 3, it takes less energy to give its electrons away than it does to try to take the other ones. So I went over an example in class talking about candy bars. So like if there is a vending machine that has a Snickers bar in it or some candy that you and a friend want to buy, but let's say they have 90 cents and you have 10 cents, it's just easier for you to say, yeah, here, take my dime. Like, what am I going to do? Like, I can't buy anything in that vending machine anywhere close to 10 cents. So here, you can have it. Okay. And then the friend will take it and then they're like, yay, thank you. And then like, you'll have their like gratitude and they'll keep that in mind, be like, that's a nice person, and then they go and buy themselves a Snickers. Now, do you get any of their Snickers? No. But you feel good about yourself. You're like, hey, I did a good deed. That's basically what this is, okay? So this right here, these groups, the cations, they don't have many electrons. It's just easier for them to give it away, all right? Whereas when you start getting from group 5 and beyond, this is your like 90 cent group, okay? This is your group that is really, really close to having enough money for that Snickers. So like, hey, can I borrow money? Can I borrow money? And then eventually someone's gonna say yes, and then they take it and then they go buy themselves their candy, right? And now this is the concept getting into how an ionic bond works, okay? So remember I said that you give your friend the 10 cents for the Snickers bar, but you don't get any. You just kind of are in their mind, like hovering there, and they're like, yeah, this person was nice. And you're like, yeah, I did something good. Okay, that's kind of how an ionic bond works. So an anion will take the electrons from the cation. So technically, it's the anion that has the 8 valence electrons, but the cation is still kind of like hovering there with it, okay? So let's look at creating ionic bonds then. Okay, so an ionic bond. So we have 2 major bonds. Right now we're focused on the one, the ionic bond. So an ionic bond is made up of 2 things, okay? 2 types of elements. We have a metal, and yes, the metal will always, always come first. Please remember metal first, and then followed by a non-metal. And then at the end, they will be stable, okay? So I'm just going to randomly pick some elements to show you as an example. So let us go back and start with what you're most familiar with, which is table salt. So if you look on the periodic table, and table salt is sodium chloride. Sodium is Na, group 1, and chloride, which is really the element chlorine, is Cl. Now, this is the chemical formula for table salt, NaCl, but notice that there's nothing for that. Uh-oh. Okay, and there's a reason for that. Because the plus means it's going to give away, and then the 1 tells us how many. So if you look at chlorine, chlorine's a halogen. It has a -1 charge. So chlorine is going to be the acceptor, and we know that it has a minus charge, and then the 1 says how many electrons it's going to accept. So we have +1, -1. Now here is where the swap and drop comes in, okay? So how do we get from elements on the periodic table into an actual bond and to be able to express that bond in a chemical formula? So one of the techniques for doing this, like I said, is the swap and drop. So you take the charges and you put it in the top right-hand corner of your element. So like I wrote Na +1, Cl -1. So when you have the numbers with the charges up here, please keep in mind these numbers right here, these are your charges, okay? So when we take these numbers and start shifting them around and pulling them around, it will no longer be a charge. You're talking about something completely different. So up here, we're talking about the charge, where the electron's going. So now here's where the swap and drop comes in. You take this number from the top, and then you pull it behind the opposite element, behind it to the right of that element, okay? So this 1 is going to end up coming behind your chlorine, and then this 1 from the -1 is going to come behind your sodium. Now, like I said, up here, we're talking about charges. Once these numbers drop to down here, so I'm going to write it again right here. So technically, you'll be left with Na1, Cl1. Now you have subscripts. Okay, now you have subscripts. But the subscript is not the same thing as a charge, okay? So when we're talking about subscripts, now we're talking about number of atoms. Now we're getting into ratios. So how many atoms of one element do we need compared to the other, to the number of atoms from the other element, okay? So notice that for NaCl, the number is 1 in both cases. When you end up having the same number, you don't write a number at all, okay? So once you have the exact same number, so whether it's 1, 1, 2, 2, 3, 3, does not matter, you do not write a number at all. Because when you reduce that number, when you simplify it, because we're talking about a ratio, okay? So like, if I say I have 2 hands and I have 2 arms. Well, okay, that means that I have 2 hands to 2 arms, but that's still 1-to-1 ratio, right? Because for each hand I have 1 arm. This is the same concept. So here's just a ratio. If we can reduce or simplify, we do. Now, what can make this actually a step easier is when you are looking at the charges up here, if you see that you have a +1, -1, +2, -2, you already know that it's going to cancel out. You already know that it's going to reduce. You're looking at the same number, so you're not going to have to write it at all in this formula, okay? So now, with the charges, keep in mind the plus says we're giving, the minus says we're accepting. So if you are, if you like math to back stuff up, to support your understanding, this is for you. If you were like, hey, that description was already good enough for me, stop, then just kind of tune out for a minute, okay? So for the Na, for the sodium, sodium has a +1 charge, and then chlorine has a -1 charge. So when you say you have +1, -1, mathematically, that cancels out to give you 0. So what this is saying is sodium had an electron, it gave it to chlorine, so now there's no extra electrons floating around. So this means that each electron has a partner, and that's what we want to happen. So this is called charge balance. You will definitely be doing this for ionic in here. Next year in chemistry, you will be learning how to do this for covalent bonds, and that's when things get a little more complicated. They definitely get complicated. But for now, we are worried about charge balance. Do these charges cancel out equal 0? Again, why do we want them to equal 0? Because the noble gases have a charge of 0, which means stability. So now let's also double check the valence electrons. So chlorine, and I'm going to do the Lewis dot for chlorine so you can see it. So a Lewis dot is just showing your valence electrons for each element. So actually, let's do it for both so you can see. So I'm going to use different color. So for sodium, sodium's in group 1, meaning it has 1 valence electron. Chlorine is in group 7, meaning it has 7 valence electrons. So you start like from the top and then you start going around, putting 1 electron per side, kind of like it's a square. So you'll be like dot, 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 dot. Yeah, okay, like that. So we have 1, 2, 3, 4, 5, 6, 7. So notice that chlorine has 7 valence electrons and then sodium has the 1, but we know in an ionic bond, the metal will give its electron to the non-metal. So the electron from sodium will go to chlorine. So now chlorine has a total of 8 valence electrons. So chlorine is 2, 4, 6, 8. So we know that sodium chlorine is a bond and it is a stable bond because it meets the 2 requirements. Are the charges balanced? Is there a charge of 0? Yes. So net charge is 0, meaning every electron has somewhere to go. And does chlorine or does the nonmetal, for an ionic bond, does the nonmetal end up having 8 valence electrons? Yes, it does. So check, check. That means that this bond is, that it's correct, that the chemical formula is written correctly, everything checks out, and that is why sodium chloride is NaCl. Okay, let's do one that's not commonly known. Okay, let's do... Okay. Let's do calcium phosphide. And eventually we will get into naming, but for now I just want to start showing you what the name looks like so you can start kind of in your head seeing what the name looks like, at least for ionic bonds. Okay, so calcium is in group 2, meaning it has a charge of +2. Phosphide is talking about phosphorus. So just a bit of information that we'll go over later. When you see IDE at the end of a nonmetal, that means it's in an ionic bond usually, or it's in a bond, okay? Even in a covalent bond, you'll see I. But I is really saying it's in a bond, okay? So it's not just phosphorus by itself, it came together with something else. All right, so phosphide, talking about phosphorus. So phosphorus is in group 5, meaning it has a -3 charge. Okay, once again, we're going to apply the same principle, the swap and drop. So we are going to take the number of the charge from the calcium and bring it down behind the phosphorus. And then we are going to take the number or charge above the phosphorus and bring it down behind the calcium. So keeping in mind, +2 means calcium has 2 electrons it will give phosphorus. -3 meaning 1 phosphorus atom can accept 3 electrons. Note, these two are not the same number. But when you do the swap and drop, it equalizes the ratio for you. And I'll show you a picture of what I mean too. All right, so this will give us calcium, so Ca3P2. All right, so for calcium phosphide, the chemical formula will be Ca3P2. These subscripts down below are no longer the charges. They are now telling you how many atoms of each you have, okay? So now is when I want to talk about these numbers and the fact that they are different from one another. So we cannot cancel out. We just have to write the number and drop it. So for calcium, so 1 calcium has a +2 charge, right? So 1 calcium has 2 electrons that it can give away. Now, 1 phosphorus atom has a -3 charge, meaning that it needs to accept 3 electrons to have its octet. So notice that only 2 sets of electrons paired up. Well, there's still 1 electron that's required. So what happens is now we have to add another atom of calcium because the phosphorus requires more electrons to fill that octet. So once again, we will add 1 more atom of calcium. But notice that now, even though this atom of phosphorus gained an electron, now calcium still has 1 more to give. So we go back to phosphorus. Let's add 1 more atom of phosphorus. And it has 3 electrons it needs to accept, which means that we need 1 more atom of calcium to make this completely stable. So here, calcium donates an electron to phosphorus. 1 more electron's donated, 1 more electron's donated. So now notice that each electron has somewhere to go. So if you look at this picture right here, notice that we drew 3 calciums, okay? So there's calcium and there's 3 of them. But then notice here for phosphorus, we only had to draw 2 because each phosphorus had 3 electrons that it could accept. So this number down at the bottom, that's what this is talking about, okay? It's talking about how many atoms does it take for these to come and bond together and for the octet to be filled, okay? So once every electron has somewhere to go, it's stable. So that's why the swap and drop works, because it does the math for you. Now, if you want to go back and track the math, make sure that it is correct, which you will definitely have to do next year in chemistry. This is what you're going to do. So calcium has a +2 charge. So keep in mind, we want these charges to cancel out to equal 0. We want charge balance. So calcium has a +2 charge. Oh, that's stupid. Okay, and when we did the swap and drop, we said, okay, well, there's 3 calciums. And then phosphorus has a -3 charge. But when we did the swap and drop, we said, okay, we're going to have 2 phosphorus atoms. Notice that when we crossed, we basically just ended up switching those numbers. And so really, we're multiplying by the lowest common denominator on each side. So we'll have 3 times +2 is +6. And then we have, and then we have 2 times -3 is -6. +6 minus 6 equals 0. Charges have been balanced. You did that correctly. Okay? So this is how we do ionic bonding. This is how we show ionic bonding. This is how we prove that the balance, that the charges have been balanced. This is very vital to know now for physical science, even more so for chemistry. We'll spend quite a lot of time on calculations similar to these. Okay, so I'm just going to show you one more thing, and then we're going to head over to Zoom because that was requested that we do a Zoom chat with like practice problems together, okay? Okay, so I mentioned that there were 2 types of bonds. We have ionic bond is one, which is what we were focused on, and that's with the charges, the swapping and dropping. And then the second one is covalent bond. So an ionic bond is made up of a metal and a nonmetal, but a covalent bond is made up of a nonmetal and a nonmetal. So in your ionic bond, you had a donation and accepting system going on, okay? Donor-acceptor is ionic bond. Covalent bond is all about sharing, okay? Atoms both throw in electrons and then they both get a full octet. So this situation would be more of, there's a candy bar in a vending machine, you have 50 cents, your friend has 50 cents, the candy costs $1, you both throw in your 50 cents, and then you split the candy down the middle. That is what a covalent bond would be, okay? So a covalent bond is when you have electrons that are being shared as opposed to taken. So as covalent bonding can get a little complex, we're not really going to go too much into it. So for covalent bonds, all you really need to know is what a covalent bond is, the fact that it's made up of 2 nonmetals, to be able to recognize on a piece of paper, like is it ionic or covalent, like if they give you the chemical formula, or you need to be able to go back and forth between the name and the chemical formula. Now, the reason covalent bonding can get more complex is because in a covalent bond, this is how like large molecules are made. Remember learning about glucose last year in biology, C6H12O6? Yeah, that's a lot of atoms in that. Okay, so covalent bonds can get really large. And then doing like charge balance and stuff for that, we don't touch that in here. In physical science, we are primarily focused on Hey, hush! Sorry. For covalent bonds, in ionic bonds, we are focused on binary compounds, meaning you just have 2 elements coming together. In chemistry, that's when you start hitting this. Okay? All right, so what we are about to do in Zoom is we are going to go over the swap and drop. So I'm going to pull up like some questions. You guys can see it with me, follow it along with me, and then like I'll show you some, and then you work out some, and we'll kind of go back and forth. And then the next thing we'll talk about is it ionic or is it covalent? So really, I'm going to give you elements or compounds, and then you're going to tell me like ionic or covalent. Okay, get some practice. So give me about 5 minutes to set it up, and I will send out. I'm going to send out the Zoom notice. Okay. And if you are here and you're like, yeah, I don't like Zoom, I don't want to use it, you don't have to, but people requested to have like a one-on-one where we could see each other and work through problems, okay? So just give me a minute and then let's get it set up.